Welcome, everybody. Super excited to have you all for this new talk for our AI for Science community. Today, we are super excited to have the Evolutionary Strategies team with us, talking about their new paper. And yeah, for those of you who don't know me, I'm Raj, one of the co-founders of AlphaKive, and we help you keep up with and apply the latest research. In case you haven't checked us out yet, we definitely suggest going to alphakive.org, kind of your go-to assistant for keeping track of the latest breakthroughs in AI research and quickly understanding the latest research papers. With that, I'll go ahead and pass it on to Jian, who has super graciously offered his time today to talk about what I think is a really interesting new paper and alternative to gradient descent. And in the meanwhile, for folks during the talk, if you have any questions, please use the Q&A feature in Zoom. The Zoom chat can get a little bit messy. So yeah, if you have any questions, use the Q&A feature and I'll be monitoring that. It'll be around half an hour talk and we'll have plenty of time for questions afterwards. But we'll also try to pause somewhere in the middle. So yeah, thanks, Jen.
Okay. Yeah, thanks, Raj, for introduction and also invite me to give this talk and giving a chance for us to then discuss something different, maybe from the mainstream kind of methods. So yeah, my name is Xin. I'm a research scientist in Coincident AI Lab. And today I'm also kind of my colleagues joined Roberto Daly and Conor Hayes. They're also co-authors of this paper. And yeah, I will just share my screen and start the talk. So yeah, our kind of paper, this one is now we have a second version. So it was initially kind of published at the end of last September. And because we tried some like gradient-free methods in like the large language model fine-tuning. And I think the story kind of begins back in 2017. It's like at that time, it's like there are a lot of like those competitions in Europe. So people are mostly using reinforcement learning to play with that. But at that time, I kind of participate in a running competition. That is, we try to make a robot running. And I tried different like methodologies that OpenAI also tested in a lot of those Atari games, which is called evolution strategies. This is quite different from reinforcement learning because it's directly searching in a parameter space without gradient calculation. And during that competitions, although I did not get the top one, whatever performance, but it's kind of like I get a very kind of, I would say, competitive performance when using evolution strategy to that robot running problem, which is in a standard reinforcement learning setup. And I realized that actually this method is much more scalable and I would say more robust than what we would expect. So that is like kind of a seed in my mind that when in this time, when I see the language model fine-tuning problems, I kind of realize this problem seems like it's also a very suitable use case for evolution strategies compared with reinforcement learning. So this is why we started to try these evolution strategies in this like seemingly impossible problem, which is trying to optimize billions of parameters in parameter space. However, it's kind of the results is quite surprising that we see actually the evolution strategy like give us a very competitive performance in this problem. And it also has some unique advantages compared with reinforcement learning. So this kind of leads to more and more effort and investment and work in this new direction. And we see a lot of promising kind of signals that we still want to push it forward further. So this is kind of, this talk will give some, basic introduction about what it is and our first paper. And yeah, I will just start from some kind of basic high-level background. And my name is Xin, and the other co-authors like Conor Hayes and Roberto Daly, they are also here. So it's kind of, if you have any question, maybe they may also be able to answer in the chat channel. And yeah, let's go. So yeah, first thing is like the role of fine-tuning in the current LLM training pipeline is kind of, it's everywhere for the like all those larger models because pre-training normally just give us a general like language understanding model. So if we want to further improve any particular in any particular aspect, it's like you want to make the language model better aligned with human preference, or you want to trigger those reasoning behaviors in your language models, or making better encoding, whatever, chatting, or instruction following. So all these kind of special requirements will require fine tuning. So if you look at all those, like the state of the art, those training pipelines, the fine tuning is always a very important step that can convert the language model from a generalist to a specialist. And only after fine tuning, like the deployment will happen, because people still want to make the model more specialized to the use cases before they really use it. So this is a step currently we are tackling. And also, why we are tackling this fine tuning, it is because people already have a lot of like error and try and realize that actually the reinforcement learning is a kind of very important part or algorithm for this step. And compare with this fine tuning in pre-training, maybe those supervised fine tuning, it's those supervised learning method is more efficient, because what we need to do is simply following the language corpus we have to generate those exact same sentences. But in fine tuning, especially in those like reasoning problems, we need a like language model to explore by itself by sampling. So the reinforcement learning is kind of one very natural method people are using. But I also noticed that reinforcement learning is actually the only method for exploration in this case. So yeah, when people are using reinforcement learning for language model fine tuning, normally what they do is like they giving the same language model, they will sample maybe multiple sequences like in GRPO, or just sample one sequence maybe in PPO. Then they will calculate like the reward of these sampled sequences. Then based on how high or how low the reward is, they will update the model weights so that they will increase the probability of those sequences that give the better reward, or if in a group size giving like a higher probability to generate those sequences that give a relatively higher reward compared with the other samplings. So the gradient descent, normally currently people are mostly using the policy gradient. So which means the gradient is not with regards directly to the reward function. It's with regards to the token probabilities, so that they will increase the probability of the tokens to generate those better reward. So they will repeat this process iteratively, and that's basically what happening for reinforcement learning in large language model fine tuning. And the reward of like this process, normally in reasoning process, we can only have an endpoint reward, which means for an entire sequence we will have one reward. And this is kind of an aspect that I feel a bit, I would say, unnatural for reasoning, because in the traditional RL setup, we will always have some step reward. So that is kind of a more fine-grained learning signal that is more suitable for RL. But currently in the language model fine-tuning domain, it's kind of very difficult to have this kind of step reward, which in this case means token reward, because normally whether a sequence is successful or not is we only know it at the end. So the intermediate steps, they can only get the same reward based on the entire reward of the sequence. So the credit assignment at token level is still a very difficult problem, which also, in my opinion, like it's not like very natural for RL. But for evolution strategies, as I will introduce soon, it's kind of we only require a response level reward. So that's a natural fit, in my opinion, in this case. So instead of this kind of, in addition to these long horizon reward issues, and if you have played with IR, I think a lot of people has experienced that the IR running is kind of, I would say, unstable. So even for the same setup, using different random seed, you will see a very high variance. And also the IR normally has a lot of hyperparameters, and it's very sensitive to it. So if you slightly change the hyperparameters, maybe your entire run just cannot bootstrap or cannot work very well. And also people has to handle those like the KR divergence constraints, because the IR normally it's because of this high variance, so the model behaviors may kind of diverge a lot to some like unpreferred kind of regions. So we still need to always monitor how far away the current model is moving from the original model. So people usually have to kind of monitor it by adding those fair divergence penalty or whatever to prevent it. So yeah, I would say basically there is some like inherent I would call like the drawbacks, whatever of RL. Yeah. So in this case, and people still want to handle, and it seems like in evolution strategies based on our experiment so far, the ES is kind of better in these experiment aspects. So yeah, the difference between the IR and ES is like in IR, we have, let's say in a traditional setup, we have an agent, which we can see it as a language model, then it will take an action based on the current policy. So here in language model, it's like it generates a sequence of tokens based on the current language model weights. Then it will interact with the environment. So in this case, we will just evaluate the sequence and we will get a reward and the state will change. But here, because in this case, it's like we have a step reward. So we'll always take one action. But in the current language model setup, it's not that natural because we will only get a reward after we generate the entire sequence, which means a sequence of actions. So for in reinforcement learning, this is kind of we don't have this kind of stepwise iteration. We only have like a sequence level iteration, and we will update the policy as I said before, update the model weights to increase the probability of those sequence or actions that give us a better reward. And in evolution strategies, the way we are doing it is very different. It's kind of population-based black box optimization algorithm that is traditionally used for those problems that has, let's say, hundreds of dimensions or whatever. And the basic idea here is like we have the original model, which maybe we call it a parent, and we were kind of mutated. So we also, or maybe we can say we add perturbations to the weights. So here the epsilon 1, 2, 3, whatever, it's kind of the perturbations or a random, you can see it a random noise vector that we can directly add to the original model weight. And then we'll get a bunch of different perturbed model weights. So every perturbed model weights kind of give you a different perturbed models. And then we will evaluate the fitness or evaluate the reward of each model. So here we can actually get a model level reward. But in practice, it can just be like, let's say we sample some sequences for a particular problem set. So yeah, and once we get the, let's say the reward or fitness of each perturbed model, then we will aggregate these kind of perturbations to decide what's the update we want to apply in this iteration. And basically this update is a weighted sum of those perturbations, and the weight is the reward of them. So if one perturbation get a higher reward, it will get a higher weight in this aggregation. Then after we aggregate all these perturbations, we will kind of update the parameters following these aggregated perturbations. Then this is like for one iteration. Then we also iteratively repeat this process in evolution strategies. So the main difference you can see here in the reinforcement learning is like we are fixing the language model. When we are doing exploration, we're fixing the language model, and we only sample in the output action distribution, or to say output token distribution. And in the evolution strategies, we are directly perturbing in the weight space. So we are also searching in the weight space. So yeah, this is the basic difference between these two algorithms. I will give like maybe more details in the language model fine-tuning scenario like later. So yeah, here is some visualization of like what happens for evolution strategies during search. So in the left figure, if you see like this lighter area is the one with a higher reward. So this like red dot is a center point for our sampling. So every time we have a base model, it's a center point, and we sample a lot of kind of perturbation or perturbed models around it. Then we measure their reward, then we aggregate the reward like the perturbation based on their reward, and update the center point. And in the next iteration, we sampled again based on this new updated center point. So we can see that actually the center point, or to say the sampling distribution, will move towards the region that has a higher kind of reward. And this red one is just in another landscape, but like this red point now it's just the best solution we see. It's like you can see the entire kind of sampling population is kind of guided by those perturbed models or sampling that has a better reward. Yeah. And yeah. And I think the main thing that our work is challenged is a traditional kind of assumption that this kind of searching algorithm just cannot scale to billion parameter space. This is even kind of, I mean, natural to me. It's like if you are directly, let's say, adding noise in parameter space in order to estimate which direction we should go, it's kind of difficult to imagine that if we have billions of parameters, you can simply sample some like noise in order to give you a learning signal. So yeah, traditionally people may not kind of believe that this kind of straightforward parameter space search methods will work in billion parameter space. But yeah, our kind of results is really surprising even to myself, is that actually it's possible that we can directly do this full parameter fine tuning of language models at this billion parameter level without any dimensionality reduction, because there is some previous work or some like recent work that literally when people try to handle this space, a very natural like thought or a way of handling it is just to reduce dimensionality, so that it's kind of within a kind of a scale that we think, oh, it's possible now to directly optimize in weight space. But kind of in this work, we show that it's actually not needed to do any dimensionality reduction, whatever. You can just directly search in this billion level parameter space. And we don't even like with a very small population size. So in our work, we only use a population size of 30, which means that every iteration, you just need to sample 30 points to estimate a very, I would say, a reliable update signal. Yeah, this is a kind of mystery we are still exploring. But yeah, this is a very kind of, I would say, counterintuitive and surprising results that really challenges people's original belief. So yeah, this is basically when we are applying ES to language model fine-tuning, how it works. So here we get a query to the language model with a parameter theta t, and then we will add like if let's say if our population size is 30, we will add like 30 different random vectors or perturbations to original model weights. And for each perturbed weight set, which means a perturbed model, we will get a reward. This reward, let's say, can be some like for some question you generate a response and you see what's the accuracy of this reward. So this reward can be whatever objectives you want to optimize. It's not necessary to be differentiable. It can be completely black box or any weird and kind of objective you can have. Then given this reward, you see here, like we have a weighted sum of these perturbation vectors weighted by the reward they received. And then we will aggregate these like updates so that the main model's weights will get updated based on all these aggregated perturbations. So the main thing is here, you see, we don't need to do any backpropagation calculation or gradient calculation. We just need to do you just perturb the weights and do an inference and calculate this simple formula. That's it. And yeah, I will give you some brief like kind of feeling of the results we get. So the first thing is that we test in a countdown task, which is usually used by a lot of like the reinforcement learning methods. And we test on different models with different implementations. And one thing I want to mention is that during our experiment, we also feel that the current like the RL implementation, their performance may vary a lot. Also, maybe let's say all of them may claim they are implementation GRPO, but all those small engineering tricks actually matters a lot. So we have different variants here, like this Z is using GRPO 0, and this V is using Vero. So yeah, we can see that at least compare with the implementations we tested, we also do hyperparameter tuning for this RL, where for ES, we simply use the same fixed set of hyperparameters. So yeah, in this experiment, we see that the ES is quite robust, I mean, across different models and gives better performance in this countdown benchmark. And also, we kind of tested in an, I would say, an uncommon task. It's like, because now we don't care about what is objective function, so we can optimize towards any objective. And this objective of conciseness task is just like to see whether you can make your model's response more concise in terms of the number of characters or number of words. So in this task, it's like the training set is so small. It's like we're only using 2 questions to train, but still we can like kind of making the model more model's responses more concise, even in a lot of different types of questions. And for this plot, it's like the y-axis is a reward, which means if the reward is higher, just means the answer of the model is more concise. And the KR divergence is want to see how the model's behavior is drifting away from the original model, because this is what R always care about. They add a KR divergence penalty to kind of force the model to be within the like a small like KR divergence from the original model. But in ES, we don't have any of this kind of KR divergence penalty. We just have the reward, which is the conciseness for evaluating the candidates. But still, yeah, like surprisingly, first thing we can see that the ES, this like square is the kind of checkpoints we get from ES at different iterations and slightly different hyperparameters. And these like the circle ones are from the GRPO, which is a signal.R methods. And we can see first thing that the ES achieve a better trade-off between this like the reward and the KR divergence. And we also see that a bit like surprising is that the IR has a KR divergence penalty, but ES does not have. But the truth is that seems like ES is better in kind of preserving these kind of behaviors of the original models, at least in terms of this measurement of the KR divergence. So this is also one thing we are kind of trying to understand. Is it because the IR trying to optimize a single solution naturally? And in ES, we are actually trying to optimize for an entire solution distribution, which means we want to have a distribution of solutions in parameter space that has an averagely better reward, because we are aggregating the information based on our sampled populations. So maybe this kind of difference, like population-based search and this like single agent search, is kind of making a single agent search more prone to, let's say, moving to some more hacked behaviors, which may have a larger hair damages from the original one. Because we also observe more hacking behaviors in this RL run versus in ES. So yeah, then we also trying to run multiple runs with, let's say, different hyperparameters for both methods. And this is like the highlighted numbers are those variance in both reward or even or KR. And one thing we can observe is like for different hyperparameters and for the same hyperparameters for different random seeds, the ES is kind of having a much lower variance across different runs. And while for the IR methods, as like usual, it will have a higher variance across different runs and different hyperparameters. So I think this is also important for practical usages, because if one algorithm is kind of less stable or has a higher variance across different runs, we may need to try more to get a lucky run that give us the best results. That is kind of increasing the expected cost. So I would say here, at least these results showing us that if let's say the two algorithm gives a similarly average performance, and we may still prefer ES because it has a lower variance across different runs, which means maybe a lower, expected cost if you want to get a reasonable result. And yeah, we also tested the ES versus IR in several like state-of-the-art math reasoning benchmarks. And in this case, we compare with almost the best implementation of IR, just particularly designed for these math reasoning benchmarks. And we can see here, like this, the bars with warm color is the ES checkpoints, and the bars with those cold colors are kind of with the best IR implementation. We pick the different ones from the literature that has the best performance in these benchmarks, and we can see the ES kind of gives a very competitive performance compared with those most advanced IR implementation. And one thing I want to mention is here, we are only implementing the very vanilla ES variant. We deliberately remove all those advanced enhancements or like those complex hyperparameter tuning, or even adding or even removing those like optimizer. We don't have any of those adapting mechanism or learning rate kind of scheduling, whatever. So we are using the same fixed learning rate with a very vanilla ES variant, and we still get a very competitive performance here. So this kind of give us hope that, yeah, maybe because now, yes, it's not really developed that further as RL, which we really have tons of mechanisms or enhancement for current RL implementations. So if we kind of further develop it, maybe we'll see kind of much stronger performance in ES. So we also kind of testing ES in those uncommon benchmarks, or those like puzzles of different types. It's like the RKGI, at least we did not see people is really using IR for it, because it seems like from some people's experience, it's very difficult to make IR work in the kind of visual reasoning tasks. Yeah, but kind of we tested yes on it, and this is the kind of the original model basically like does nothing in this RKGI, but after fine-tuning with yes, we kind of we can get a lot of questions right and reach to a like very different level of capabilities in this benchmark. And we also try Sudoku, and in Sudoku, the original model is also barely like doing nothing. And after fine-tuning with yes, we get quite good accuracy. So all this testing is just to see whether the ES can be generalized to different problems. And it seems like, yeah, it can. And also there is some additional discussion maybe we can also leave for later, because I think time is almost there. So yeah, I think the main thing I want to mention 2 points between these, like the two IL versus ES. The first point is like the key difference here is like we are doing parameter-based search versus action-based search. So in ES, the difference is there we are indeed sampling different parameter set. So we have a base language model, then we have a paradigm-based language model to explore. So if we look at it from the IL perspective, it means it's not like we have fixed during exploration, we are not like fixing the policy, then sampling based on these policies output distribution. We are really sampling new policies in ES. But in the original IL setup, we are always like, when we are doing exploration or sampling, we are fixing the current model weights, but we only sample in the output distribution of this policy, which means that we are not really sampling new policies. We are sampling actions based on this policy's output distribution. So this is the main difference, and in my opinion, between like the parameter-based search versus action-based search. So if our reward, let's say later, is model level weight, which means we are really measuring the properties of the model or some kind of special objective that is based on the model states, then the IR, at least the current IR setup, just cannot work there, because the IR search does not change the model. It's only searching in that model's output action distribution. But in ES, we are really sampling new policies and new models. So that makes a key difference here. And another thing is like people are always like interested, like gradient free versus gradient based. So in my opinion, I think both methods has like pros and cons. So for gradient free, definitely like get rid of the backpropagation, where like needs much less implementations and also a much lower GPU memory requirement. This is really kind of a compelling advantage. And also in my opinion, because normally these gradient-free methods, they are based on directly perturbing the weights in the weight space. So it will give us more global search compared with like gradient-based methods. Like we will only do those more fine-grained local search because you get exact gradient signals, like with regards to like reward function. But in my opinion, it's also a more efficient update if, let's say, your target is just to reach an exact optimal point at this local search region. Then if you get the gradient and you don't care about computation like burdens, then it's a more efficient update, in my opinion, at least locally. So, and also you can do more fine-grained local search. So these two methods has both pros and cons, and which we can also discuss and explore. And yeah, we also have some follow-up works based on the first work, but yeah, I want to cover them today. But basically, so we are trying to, let's say, we know now we can try to optimize towards different objectives that we cannot image before, because now our method completely changed. Like we can optimize for metacognitive alignment, which means that we want the model to know what it knows. It's like the alignment here is measured by the alignment between whether the model's answer is correct compared with whether the model thinks itself can answer these questions. So this kind of model level properties is difficult for IR, or even not straightforward for IR to implement or to try. But for ES, we don't care. We can always measure and optimize it. And also because we don't need to calculate gradient. So now it's possible for us to directly optimize those quantized models in quantized space, which is very difficult to get gradient because all those weights are integers. And also, we are trying to do some theoretical work to understand why it's even possible to only sample 30 times to optimize billions of parameters. So we call this kind of fun, even it's not a curse of dimensionality. It's even a blessing of dimensionality, which means that for larger models with more weights, the intrinsic dimensionality may even be like lower, which is even easier for ES to optimize. So all this like follow-up works kind of give us a lot of interesting extensions. And yeah, I think the time is almost there. So yeah, feel free to reach me at this email address. And here is the QR code that you can get a link for the paper, our source code, and we also have a blog kind of summarizing all these follow-up works. So yeah, thanks everyone for your time. Yeah, feel free to discuss and ask questions and even challenges this kind of new direction. So yeah.
Thank you so much. This is awesome. Yeah, a lot of discussion already happening in the
Oh,
chat, and you seem like you're in a great flow. And we are lucky to have Connor and Roberta helping out. So
oh, great,
did
great.
interrupt you, but yeah, I guess we can get started. I mean, we can start with some pretty quick, simple questions first. Somebody was asking about the mutation algorithm that you use. I'm guessing it's pretty straightforward, just random normal perturbations to the
Okay,
parameters.
yeah. So yeah, so I can ask this. Oh, okay. Okay, yeah. So
Yeah.
for the mutation, yeah, for the mutations, currently we are using a very simple method. But yeah, but I will also mention one like special point here. So first thing is like we are trying to add a completely random like vectors to the weights here. So this epsilon here, you can see it's just like sampling from a Gaussian distribution. Like we like different we also don't have any restrictions, like I mean for in the covariance matrix. So every dimension we have the same variance, or to say scale, when we sample the Gaussian noise. And so you can imagine that if we have billions of parameters, and in every dimension we just independently sample one Gaussian noise, that's it. And also because I mean for convenience on implementation, our current implementation has a slight different, I would say, trick or whatever, is that in every layer, we will kind of reinitialize the random seed. So there is some correlations of these noise vectors or random noise vectors across different layers. And this also gives us maybe a potential later for us to speed up it further in the CUDA level, I mean, optimization, because kind of the noise patterns are slightly repeated across layers, but still you can kind of treat it as almost IID. So yeah, for the mutation, it's quite simple. We do not have any fancy mechanism added here, but I agree that this is an aspect that we can further improve a lot in the future works. But now I try to deliberately keep it simple because we want to see what's kind of the effect of this fundamental method. But yeah, you can have, like, let's say for different dimensions, you can have different scales of this noise added based on the original weight scale or whatever. Or even for some dimensionalities you think it's not necessary to even change them or touch them, then you can just add a very small kind of noise scale there, or even remove that noise perturbation. So yeah, that's the answer.
Yeah, makes sense. Raphael, are you here? If not, yeah,
Yes, I'm
Raphael is.
here
Oh,
actually.
yeah. Sorry, go ahead.
Yeah, my question, was more of an intuition. I mean, I appreciate all the talk. I was basically wondering, is how does the like ES approach relate to mixture of expert architectures? Like, is there some relationship you see in like to train basically sort of
Mm.
mixtures of experts with this, like some
Yeah,
difference?
I think, yeah, at least in my opinion, maybe people may feel, oh, mixture of expert is like we also have multiple models and we kind of aggregate them. But I would say they are still orthogonal, because the mixture expert is in the model architecture aspect. It's like we have multiple models and we kind of doing an ensemble there. But yeah, maybe the ensemble part is similar to the kind of aggregation part in ES. which is like we trying to aggregate that perturbations. But in my opinion, aggregated perturbation versus like aggregating the directly, I mean, using those models in inference is different, and they are kind of complementary to each other. It's like you can also using ES to optimize a mixture of expert model. So in my opinion, seems like they are similar, like both of them has different perturbation. But in ES, for those like different sampled perturbed models, our purpose is not to use them together. Our purpose is to kind of filtering out those better ones so that we can move our model update towards those better ones and try to push it away from those bad ones. But in the mixture of expert, my feeling is that we are really trying to make use of all those experts. So each one of them has different unique advantages so that you can kind of use them as needed or accordingly. But in ES, all these sample different perturbed models, our purpose is use them to explore the weight space to get a sense of how the weight space landscape is looking like, then trying to move our model towards those regions that has a better reward. So I would say the purpose of these different perturbed models or expert is different. And yeah, I also don't want to mix this two kind of aspect. The mixture of expert is in architecture, is an architecture, and what this ES is just a search method. So the ES can also be directly applied to mixture expert if for your second kind of question. Yeah, ES can be directly applied to mixture of expert. And you see the way ES is limiting. We basically just perturb all the weights of that model. So we don't care about the model architecture. It can be whatever architectures. And yeah, hopefully that kind of answer your question.
Thanks. Yeah, I think I got the intuition, like more adaptive, basically, it seems to understand, I'm understanding.
Yeah, and also they are in different aspects. So this ES, you can treat it as more like a search method. So also sampled models is just helping us to get some sense of what weight set perform better in this reward. Yeah. And for mixture of expert, we really want to make each expert as good as possible so that when also we want to trigger a synergy between them so that when we are making them working together, then we get a better general performance. So maybe this is also a difference there. Yeah, but awesome. I think one point I think I kind of reminded me here is like it's also interesting that I agree because we have a population of perturbed models. Maybe we can also figure out how to merge them, like in a way similar maybe to make the expert to make use of this information because anyway we sample auto models, we know their performance or strengths or weakness. Then yeah, maybe we can even extend this kind of line of work to naturally make some of these perturbed models become part of the mixture of expert, like become one expert, then we merge them. That is also one very, I would say, promising research direction. Yeah.
Thanks a lot.
Mm-hmm. Awesome. I guess kind of related to that, Gabriel in the chat was asking, like, is ES always applied in post-training or fine-tuning only? I know you had a slide at the start. Yeah, we kind of talking about it, but yeah.
Yes, this is, I mean, at the start, we only try in the post-training because we see that the IR is used there. So we assume that's kind of, because ES is kind of can resolve, in my opinion, the cases that IR can resolve. So if IR is applied, then I would kind of expect ES to also perform competitively there. So this is why we start from fine-tuning. But yeah, we also have some initial experiments, but still running for the pre-training thing. And actually, the ES, I would say, is also possible to do pre-training because I think another reason why we are like not starting with pre-training. First thing is it's expensive. Second thing is that in pre-training, because I think the target is slightly different. In pre-training, mostly what we need to do is just to follow the exact sequence that we already have. So maybe in my opinion, in that case, if you can do the supervised learning, that is a very natural, efficient way to do it because anyways, you are supervising it. But for ES and I think the strength here is like the algorithm itself can search and explore. So let's say in the reasoning task, we don't need to really to define what is your reasoning path or thinking process or the sequence that you have to generate. We just care about the final reward. So whatever thing you generate, if it gives us a better reward, then it's a better like behavior or model weights we want to encourage. So in this case, the yes and I is more natural that it can explore. But in pre-training, mostly we really don't need to explore, right? We just need to follow that predefined sequences to keep just making the model to generate those sequences. So in that case, like the supervised learning is also a very natural kind of way, in my opinion. But I agree that maybe instead of using supervised learning, using ES can give us some different dynamics there. Let's say the models can be more general, whatever. Like we don't have a conclusion now, but we have some initial tests using ES to do the pre-training, but clearly in a smaller scale size. But yes, indeed works, and it can train a model from scratch. So basically, you just change your reward to kind of those whatever entropy, cross entropy, like whatever, like based on the sequence you want to generate or learn. So yeah, the answer is we have tried ES in pre-training and it is working, but it still have need more experiment to verify whether it's kind of better than supervised learning or not. But in my opinion, yeah, it's possible. And we also, yeah, maybe that case is slightly different compared with the fine tuning, which we may need more explore, especially in these reasoning tasks. So yeah.
Just as a follow-up, thanks for your answer.
Mhm.
You think it's fair to say then that in post-training you might be getting a boost because your base model is sort of acting as priors on your model
Mhm.
distribution
True.
and your posterior for ES?
Yeah, I agree. It's like I would also say like the fine tuning because we are kind of I would say like we are saying in our follow-up work we see that actually the fine tuning landscape has a very low intrinsic dimensionality, which means this problem is actually not as difficult as we thought. That basically like I think reflects what you just say. It is because in my opinion it's also like in the pre-training phase the model already learned a lot of different capabilities or skills. But in the fine tuning, maybe what we are doing is just to unlock them. So that is maybe easier than learning from scratch. So yeah, maybe that is also the reason why this like the ES or I this kind of exploration based search can for different tasks they can always work because the model itself has already encoded a lot of skills or capabilities that may need by different special tasks. And what those search algorithms are doing, just trying to unlock them. But in our initial pre-training experiment, the yes indeed works. So it's kind of, and also with a very small population size. So it's kind of making me even more, I would say, confusing. Is it kind of this low intrinsic dimensionality or the learning of a model weights this task itself is not as difficult as we thought, especially for those larger models. It's like we always think larger model, more weights means a more difficult search problem in parameter space, but it may be opposite. It's like if we have more weights, and it means that basically you will have more opportunities to sample a better weight set. So if you see the nature of ESNI, what's the nature of this search? It's just like your chance to sample a better solution. That's it, right? If you can sample a better solution, you can move your center point or move your policy, then you can start to learn. So the probabilities to sample a better solution, either in action space or parameter space, is a key of learning and searching here. So if in pre-training like case, we also see ES can work, which means that actually it's not that difficult in that large parameter space to sample a better solution. It's like because maybe the parameter space is larger, so we have a lot of like inherent representations already encoded there, and any samplings will give you a very good chance to kind of trigger one representation that gives you a good better performance in the current reward. Then your learning will start to bootstrap. So yeah, I think that's a very fundamental question about learning.
Thank you.
Oh, Raj, you're muted.
Oh, Parth, are you still here? Um,
He's in a cafe, he just said.
oh, okay, okay, awesome. Well, Part's question was, how does the reward variance for perturbations look like across the task?
Uh, can you elaborate that question a bit more? What do you mean by the reward perturbation?
Yeah, I'm guessing what they
Okay, let
mean
me see the
is,
question.
yeah, it's a little bit up top in the chat, but I'm guessing what they mean is, for ES, you make all these perturbations and you compute the reward for each of them. Like, is there
Right.
usually a lot of variance among the reward for each
Oh,
of the
okay.
perturbations?
Oh,
Yeah.
yeah. I think that's first thing that's really basically like is affected by this sigma. You can see my cursor. Cursor.
Hmm.
Yeah, yeah. The sigma here is kind of you can see it's control the scale of our like perturbation or these random perturbations. So yeah, basically the variance of this kind of correlation reward is kind of affected in at least within each iteration is affected by two factors. First thing is like which stage currently your search is. So normally when you are reaching a later searching stage, you are reaching a region normally that has a flat kind of landscape there, which means you add the same level of random noise perturbation, you get less variance in performance. That's what we observe. It's like in the later stage, it's kind of where the algorithm will move to some more flat regions that you add the same kind of scale of perturbations, but you observe less change in behaviors. And in early stage, you will see more variance of this reward in the same iteration. And second thing is like how you set up these parameters. So yeah, this is very naturally. If you set this sigma to be larger, then you will see more like behavior difference because you are changing the weight more. And if you set it smaller, then you will see less. So this is kind of the two factors: is the stage of the search and also your hyperparameter setup will decide it. And for setting up this sigma, it's kind of there will be some I would say a sweet kind of range. Is that you don't want the sigma to be too small so that like you did not really change the behavior of model. Kind of you are wasting one inference. It's like if your sigma is very small, then all the perturbed model they still have the same behaviors compared with the original model, which like we are wasting inference. And if you set up like to be too large, you are completely disrupting the original weight that learned by the original model. So you just get those nonsense tokens. So there is a kind of a range that you can easily test it for your problem that what kind of scale. I think also for the models that you are testing, like what kind of range of this sigma or random perturbations can give you, let's say, a change in behavior for every perturbation, but this change is also reasonable. So yeah.
It's
Awesome.
actually related to my question, Raj, if you want to cue me
Yeah,
up.
go for it. Go for
Okay,
it.
cool. Yeah, so it looks like the evolutionary strategy you're using um, is I'm not surprised that it's similar to the gradient descent results because
Mm.
it's if you can imagine a fitness landscape that you're searching on, which is effectively what you're doing, um,
Mhm.
you're really casting a small net on the fitness landscape. You're not making huge changes to the population.
Mhm.
And
Yeah.
I also noticed that based on the size of the population you've been running against relative to the size of the parameter space, um, you probably aren't even in the neighborhood of being able to explore large
Mhm.
parts of the fitness landscape. And I can see that that's by design. You're really like, doing a really nice, rigorous side by side, apples to apples comparison with RL, which is really nice. But I'll bet you've started to think about what happens when you increase the population size. And I'm curious, like, how big can you practically go? While I was listening to your talk, I was thinking about tricks that you could use to try and really expand the population, the effective population size, which is what biologists call it,
Mhm.
for your evolutionary search. You know, obviously, I hope you're not just keeping an actual copy of the policy for every member of the population. You're
Mhm.
keeping track of the diffs and applying them in some really efficient way at inference time. But I've been thinking of like linear algebra tricks that could massively
Yeah.
scale the effective population size. But I'm wondering, like, yeah, are you thinking about like what happens when you go one, two more orders of magnitude up in population
Mhm.
size so that you can really explore? And then the sec related question is, have you thought about other reproductive mechanisms other than the random mutation that you're doing
Mhm.
now? Because I mean, this is a great example of learning from biology. The most powerful mechanism ever invented by meta mechanism invented by
Mhm.
evolutionary biology is sexual reproduction.
Right.
It's not clear why it's so powerful. There's two competing theories, but it is undeniably the most powerful evolutionary engine ever created. And yeah, I we had dinner, Raj and I, at NeurIPS with Jeff Clune and Ken Stanley,
Mhm.
and we had a fantastic conversation about neuroevolution. And yeah, it's such an early time for this field. You're probably doing some of the most interesting work that could possibly be
Yeah,
done.
but this crossover is indeed a question that I
So
cannot
interesting,
explore for
right?
years.
It's so interesting. What's really
Yes.
special about these language models that you're working with
Mm.
is that, and artificial neural nets in general, is that phenotype and genotype are the same thing. There's no distinction between the genes and the actual organism. You're actually operating in the same space.
Yeah.
And and so like there might be some amazing shortcuts you can take in
Mm.
your evolutionary search, but like no one, I haven't heard any, like this is so unsolved. And I don't know, this is a generic question. Have you started
Mhm.
to think crazy ideas about ways
Uh,
to really explore
yes,
this?
yes. Yeah, I think I have a good answer. We have done a lot for both questions. So the first question for population size, I think what actually you care more here is not really the population size, because what you care more is like whether we can do, let's say, a search in a large region or
Population
even more
size only
global
matters
search,
if
right?
you get combination, if you get the equivalent of
Yeah,
recombination.
yeah, but I think first thing is like for these search regions, actually the population size, in my opinion, is more to at least in this like the ES setup. If you have, let's say, the same sigma here, which means already define your explore region. So you have more population size, just means you sample more densely and in this region, but it basically just gives you more accurate estimate of the direction you should move within this region. But
Mm.
if you really want to expand your kind of search engine, you need to increase this sigma, or even let's say in this ES case, because now we only have a single center point, right? We just sample and shrink, sample, shrink. You, in order to really do the global search, we need to do something more similar in the traditional evolution algorithm, which means we always maintain multiple candidates. So here you can see we maintain multiple this center point. Then every center point may be doing some local search by this kind of perturbation around it, then shrink. But then how can they interact with each other? It's the
Right.
second point you just mentioned, the crossover. So we need to cross over this kind of center point. So this is why I would say the merging of these models is promising direction, because traditionally people also really did a lot in this new evolution, how to cross over two model weights. That's a very difficult question. It's
Yeah.
because the model, whether we should directly merge them or cross over them in the weight space, if we are cross over them in the weight space, we are easily get a problem. Maybe we call it competing convention, whatever. It means that for the same behaviors, we can have very different combinations of those weight values. They are doing basically in output, from output perspective, they're doing the same thing. But because in the weight space, we don't care like if we switch to a node or whatever, right? But when you cross over them, this alignment of this weight kind of crossover is very difficult to do. You are kind of easily breaking both architecture or structures you learned there. So in I think in biological is like our gene when we are doing crossover, those like the positions of the different alleles, whatever, is kind of decided. So they only switch in the same position.
Right.
But in this neural network weights, once the two, let's say two center point or multiple center, they diverge to different regions and they kind of evolve by themselves.
Mm.
Let be, and we try to cross over them. This will be a problem. Or maybe a simpler thing is that we need to kind of uh, for those like the weights or candidates we try to cross over. make sure they are kind of perturbed or mutated from the same origin. So that maybe they have a better alignment in this weight pattern, then we can try to cross over. Or maybe you see the Sakana AI, they also did something. They try to merge models in like block level. Like we directly exchange the blocks or layers. That's also one thing to do crossover. But I completely agree with you that the crossover is the power of evolution compared with mutation. But in ES, you can see it. Also for every perturbation is a mutation, right? But you see this aggregation part, in my opinion, it's also a sort of crossover, but it's just a crossover among the entire populations. So it's not like two candidates they cross over. It's kind of the
Yeah.
entire population they try to cross over with each other. So try to estimate what can be a better aggregation. So yes,
Yeah.
yes, I would say it's still doing some, but this is just local crossover because everyone is a small mutation from the same candidate. But I agree with you. In order to do this more interesting global research, we really want to cross over two candidates that is really far away from each other, let's say in terms of behavior. So this is the power of crossover. And I also actually did some even theoretical work previously in the neural after search by proposing a new crossover operator. So my understanding of the power of crossover is that it's actually automatically detecting what should be the part that we should keep them intact versus what should be the part that we should need to explore. If you see two candidates, both of them has a good fitness that we want to make them reproduce, right? But maybe their behaviors are different, but both of them have strengths and weakness. So when we try to cross over them, if you well align their like representation or these encodings, then for those encodings they are shared with both of them, we want to change them in crossover. This is an automatic mechanism to detect what is the
Yeah,
part
very
that both of
interesting.
them share. And if the two components are very different, then we start to kind of do a random switch between them to explore in that region, right? By try different combinations.
Yeah.
So that is kind of automatically defining what region we should explore, what region we should keep intact in crossover. That's a power, in my opinion, of this automatic adjustment in crossover. So yeah.
You know, do you think that we might need to start from scratch, adding a mechanism that enforces modularity so that you can
Yes.
take advantage of that rather than trying to retrofit the genome
Mhm.
of a language model, which is probably just a wiring mess. You know, Jeff Kuhn
Right.
did a really interesting recent paper measuring that, I can't remember his term for it, but measuring that problem
Mm,
of noisy wiring, you know, over it's like
mm.
unnecessary complexity. Could we actually evolve a network to have a modular structure which would enable that crossover to actually work?
Yes, I think this also one possible solutions because that modularization will help us to do this kind of alignment during crossover. I always feel how to solve this alignment issue during crossover is a key
Hmm.
to kind of make crossover successful. We don't want to kind of mess up the position or whatever. So yeah, the modularization, I
Hmm.
think that's one possibilities. Then we can really easy for us to kind of align for the same like corresponding module between these
Yeah,
two
yeah.
candidates, whatever. Yeah,
Like a good
I think.
intuition is that a virus has a genome of only on order 100,000, letters,
Mhm.
and yet, the huge diversity of what they're capable of with,
Mhm.
rapid evolution, like should kind of indicate that there's got to be a powerful way. There's got to be a very powerful
Yes,
way to harness the population.
yes, yes. I also hope that we can do more global search instead of like a single, like
Mm,
I mean regional local search here,
mm,
like
mm,
in
mm,
ES. Yeah, yeah,
mm.
yeah. I completely agree.
So cool.
Just
Yes.
wanted to jump in real quick to the conversation because one thing, John, when you mentioned earlier, opening up the model space or searching more of the parameter space, that could happen. So the difference between something like gradient descent and this kind of ES algorithm here is like you, when you're doing ES type of algorithms, you can actually search, I'm calling it the posterior distribution, but whatever you want to call it, you can search the space and find things like multimodality. There might be parameter spaces, regions of parameter space that yield same rewards with totally different combinations of parameters. Uh,
Right.
so you can actually start to understand more about the global the global geometry of the posterior parameter space than you would if you were just doing gradient descent, which is just going to take you to a local minimum and stop, right?
Totally.
Yes. So for this point, we also see in some of our follow-up experiments, we see that, let's say, the behaviors of the two models are very similar when we obtain from RL, which is gradient based, versus in ES. But we see their weight patterns. They are quite different. It's like compared with the original model, the solutions found by RL is, I would say, very similar in terms of this, like the weight norm or whatever. But the one found by ES, the difference between the weight and the original model, like it's quite almost like 100 times larger than compared with the gradient-based ones. So they exhibit maybe similar behaviors or similar accuracies, but they are very different in the weight space representation, which is kind of just now to that point. Yeah, it's possible for us to discover some very different bit like weight combination, whatever. Although they have showing a similar behavior, but this kind of pattern is still very interesting. It's like it's possible to achieve the same goal, but in a different way. So
I would be
yeah, that
curious.
diversity interesting. Yeah.
Yeah, I would be curious to know, like, if let's assume gradient descent based methods like RL got you a certain, like you're saying, gave you some weights, and you got a model that responded well to your reward signal, and then ES, I don't know, let's say if we found like even three different, very different model weight combinations that got you a similar result. Then my question is, do any of the very different ones generalize differently from the RL based one outside when you have out of distribution data coming into your model?
Yeah, I think that's kind of we test a little bit. Let's say for small models, seems like because that ES really drift much farther from the original model, so the performance will drop slightly larger compared with the I1, but only for small models. It's like for 1.5 billion, we see some this kind of drop performance in those, let's say, the output distribution tasks. But in for like when we increase model size, let's say to 3 billion, it's kind of this kind of thing almost disappear. I'm not sure it's because the larger model size will kind of tolerate more of this larger drift in the weight space, or yeah, it's because just like larger model is more difficult to like overfitting in the training, because it's also, I don't know whether it's because of overfitting whatever. Yeah, but this is the thing we are still explore, and at least from like I would say the distance in the weight space, I would expect like the ES solution to, let's say, to even have a more different behavior. But yeah, I think it's very similar to what that gradient based one can get in terms of the final performance. So yeah, we are still exploring and we don't have a conclusion yet.
I mean, the most expensive, insane way to do this would be to do ES on training data. So training data has all the properties you want. You can cut them, mix and match them. You can do like recombination.
Mm.
You can synthesize, you can generate, like, imagine you're doing ES
Yes.
on the training data landscape. It's like very expensive, but like theoretically, that really would work.
Mm.
If you assume that you can get to any model via training, right? If
Mhm.
if the space of all possible models, can be obtained with some combination of training data, then in principle, training data, along with initialization, clever initialization staging,
Mhm.
like could actually get you the kind of shortcut that I'm dreaming of, but
Mm.
computationally insane. You don't want to do this.
Yeah, but maybe people will do it. Yes.
But I could imagine a nice academic study that does a toy version of this problem that
Mm.
would probably be able to really test this hypothesis. You
Mm.
you could really tease out the difference between ES on parameter space, ES on action space, and ES on training data.
Mhm.
Yeah.
Right. And yeah, I do agree. It will be more interesting if we can observe some different behaviors or
Mm.
I have different learning dynamics in this like parameter space-based search compared with the gradient descent, because people are always using these gradient-based ones. But now that we have more, I would say, brute force method is like directly part of the way. So hopefully it can give us some new learning dynamics we can observe. Yeah.
Mm. Or you just throw LLMs at everything and then do distillation.
Yeah.
Awesome. This has been so interesting. Thanks, Shin. I didn't even realize that we went like way over time. I
Oh,
really appreciate you guys staying over. This has been awesome.
okay. Yeah. Thanks, Raj, for hosting, and thanks for everyone and for these fruitful discussions. Yeah. Let's kind of follow up more. If you have any questions, you can feel free to contact me or my colleagues, whatever. So yeah,
Yeah,
I'll be
definitely.
happy to
Thanks.
discuss.
You're
Thanks,
working on the
everyone.
most interesting stuff. This is the most interesting.
The most weird stuff, I would say.
Yeah, which makes it the best.
Yeah, thanks for your comment.